Okay, then let's start. Good morning, everybody. Good morning, ladies and gentlemen. My name is Thomas Heber from Composites United. I welcome you to our Composites United series Webseminar Wednesday. It's the first we do after a little pause, a little summer break. And today we have also a special. It's not only the Webseminar Wednesday today, it's also it's also a part of the Fraunhofer IKTS seminar series NDT for Industry. And also our speakers today. Welcome Kilian Tschöke and Martin Schulze. Hello. Are from Fraunhofer IKTS. Good morning.
Morning.
And Fraunhofer IKTS stands for Fraunhofer Institute for Ceramic Technologies and Systems. But there's also a very big Fraunhofer part at IKTS that doesn't deal with ceramic technologies, but more with non-destructive testing. How that belongs together, you will tell us in a minute. But today you talk about from the fiber to the component to reliable structures, overview of current non-destructive testing and monitoring techniques for CFRP. And I think, Martin Schulze, you will start from fiber to the component, and after that you hand over to your colleague, and Kilian will then follow you with from component to reliable structures, when I got this right. Okay.
Correct.
Welcome, you both. The stage is yours, and have fun. We see you again you see me again in half an hour.
Thank you, Thomas. Hello, everybody. Nice to meet you here in the combined Webseminar Wednesday together with Fraunhofer IKTS NDT for Industry series. My name is Martin Schulze. I'm from the eddy current group of the Fraunhofer IKTS, and I will show you some interesting applications and non-destructive testing devices and technologies from the eddy current inspection technology. So I will start my talk with this introduction slide. So here we see the components, the stages, how to manufacture a CFRP component. It starts at the roving, then goes over the textile, the preform, the RTM, and then the finished component. And we want to inspect the whole carbon fiber value-added chain. And this is possible with NDT technique based on high-frequency eddy current technology. I will start with a short introduction with a short first inspection system. This is the volumetric eddy current array. And then I will continue with 2D inspection systems with an inspection system that generates polar diagrams to analyze the fiber orientation. We have solutions for analyzing 3D parts, so quite finished component. And we can also inspect the whole non-crimp fabric at 101 inch with such a eddy current inspection line. But first of all, I will introduce with some basics. Eddy current method works is an inductive method, an electromagnetic method. We induce so-called eddy currents by an excitation coil into the electric conductive material. Then there in the material, based on the conductive properties and also dielectric properties, these so-called eddy currents occur, and the field that surrounds these eddy currents will be picked up within a secondary coil or even with the same coil. We have this formula here that describes the penetration depth. That's a function of the conductivity and the frequency. The magnetic permeability of the carbon fiber material doesn't interest, so it's 1. So here you see that the frequency, by changing the frequency, by increasing the frequency, we can optimize the penetration depth based on the conductivity of the carbon fiber. Here you see typical conductivity of aluminum, so that's 37 megasiemens per meter, and the graphite is 10 times slower, the conductivity. And here, when we have a look at the carbon fiber, based on its anisotropy behavior, we have different conductivities along and across to the fiber. This so-called anisotropy comes from the contact points. So we have a resistive part in the fiber, and also capacitive components that describe these anisotropic behavior of the material. To analyze these carbon fiber materials, we have an own device, this Eddicus Pro 2 OEM. So this is a typical eddy current system, but with a unique feature, that's the high frequencies. So we can measure with frequencies up to 100 megahertz. And because of the low conductivity of the carbon fiber material, we need these high frequencies to get a sufficient amount of energy into the material and to get a significant response out of the material that we can measure. Typically, we use these anisotropic probes. So we have a transmitting and receiving coil. And by rotating the probe angle, we can focus into different layers, different orientations of the probe, of the sample, and can also optimize the sensitivity of our system. First of all, I will continue with the roving inspection. So also, therefore, we can use the eddy current technology. Here you see a very simple laboratory device. So this is a coil. The roving goes through the coil, and we analyze the electric parameters of the fiber. Here, this is a very, very simple or a demonstration sample. So we make some knots into a roving, and by the summature of frequencies, in this case 5 to 17.5 megahertz, we generate an integral over all frequencies. Then here you see these knots very, very easy. But this method is also able to show the coating of or to measure and to characterize the coating of such a roving. And actual developments are these so-called volumetric eddy current array. So here we see many, many coils that are surrounded this tube-based sensor. And by changing the the transmitting and receiving configuration, we can generate such like a volumetric image of the roving. So that's our actual developments. And we tested these probe at an aluminum pipe. Here we see some boreholes into the pipe and a rotating image. So we can also actually generate eddy current 3D scans of such a pipe. To analyze preforms and even RTM and also finished parts, so the earlier we found defects, the better. We have such 2D Cartesian robots with an integrated eddy current probe that can scan even over 3D parts. Here we have some examples. So we have also other devices. Such a device is in the laboratory at BMW. They analyzed their i3 BMW model, the electric one, with this device. And it was focused to monitor defects in the non-visible RTM. And this is an example. So we see missing bundles even in the non-visible third layer. And also marshes and wrinkles can be analyzed. So this is the picture of the textile, and here we see the eddy current C-scan. This device was modified to, or the shown devices were modified even to such a flexible scanner. So its main feature is the possibility to suck on a structure, and then you can obtain an eddy current C-scan. With this device, with this type of device, we are able to monitor wrinkles and gaps in up to 11 layers. So the device is able to monitor 800 by 600 millimeters and has this nice control cabinet, so you can use it in the laboratory or even in the field. And here we see some examples. So behind this place, so this is a typical structural health monitoring or a demonstration unit. There were some SHM acoustic probes behind the or the bottom of the specimen, and we also see the stringer connections here in the eddy current C-scan. To analyze small parts only for its angle or layer orientation, we have this so-called Edicus Polar Lab. It was also developed for BMW, so they had the problem or the task to monitor the fiber orientation in these small specimens. Here we see eddy current C-scans acquired with different probe orientations. You see that there is a different behavior in the C-scan when we rotate the probe. And this is the device. And we wanted to eliminate the cost-intense computer tomography-based inspection of this type of specimen with this device. It works at frequencies from 10 to 100 megahertz. We can acquire 4 frequencies in parallel. It only takes 6 seconds and has a high accuracy. It can work in so-called reflection mode and also in the transmission mode. Here we see an example how it works. So the probe rotates, and in parallel the polar diagram will be acquired, and you can see here the analyzed fiber angle of this small specimen. So we have 3 fiber orientations, and there's a little displacement in the fiber. If you want to monitor the 3D, if you want to monitor 3D parts, then we can also use robots. Therefore, I want to show you the process of digitalization of an unknown component, how to create the path, and how we generate these eddy current 3D C-scans. So first of all, we digitalize an unknown object with a line stripe camera. Then we optimize the 3D part. So we close some parts of the object. Then we generate 3D or a region of interest onto this part, and say, okay, we want to scan from the top to the bottom and so on. Then there's also a collision optimization. Then we scan over the surface, and here we get the 3D eddy current C-scan, and we insert this wrinkle in the 11th layer. Yeah, so this was clearly visible with this robot-based inspection. Yeah, we've delivered some of these devices. One is in Stade as well at the DLR. Also, one eddy current robot cell is placed in Korea. And here we have some also interesting or nice examples. So this is a stringer. We have overlapped areas of non-crimp fabric. And we also see the stringers here in this direction. So, as you remember, the rotation of the probe takes some time, and therefore we developed a so-called eddy current array, so a small array that where the receiving combination rotates over the transmitting coil, and so we can generate different orientations simultaneously. That increases inspection time a lot. So the last but not least is the novel developed eddy current array that inspects up to 101 inch of non-crimp fabric. So that's a typical size of a machine. So this machine is developed by Karl Meyer-Malimo in Chemnitz. There are different fibers were laid up to 5 fiber orientations were laid up and then stitched together to a so-called non-crimp fabric. And also here, this for this application, we use this anisotropy of the textile, and we thought, okay, we have to generate an array of many coils to measure on these fabric. So we have a transmitting line and a receiving line, and we generate different sensor combinations. And this is the actual state of the art. So the eddy current array. So we have these 2 PCB boards. There's an overlapping area here, and we have different sending and transmitting lines, and we generate different combinations to optimize the sensitivity in different layers. So we have 12 of these arrays, so 24 PCB boards, and we can generate 128 individual transmitting receiving combinations on one PCB. In sum, there are over 3,000 eddy current channels at 101 inch. And there's a multiplexing rate of around about 100 kilosamples per second. So that's mostly the fastest and longest eddy current array in the world. So that's the device. We have 4 eddy current channels in this cabinet here. Here's the eddy current array. We have a mechanics to lift up the whole array. That's an ATEX certified HMI, and the PC that is where all the calculations and the parameterizations were done. Here we see the system in the field. So we have a little lift off, so we don't touch the surface, and in parallel at up to 5 meters per minute. We can generate these eddy current C scans. That's quite impressive. Maybe somebody of you know that calibration is a problem or is a challenge on isotropic material. It's not a big thing, so you make a measurement in air and you make a measurement on the component. But here at the non-crimp fabric, at the NCF, we see this behavior. Because of the high frequencies, we have electronic phase shifts, different amplitudes based on the connection of the array, so it's a daisy chain. And here we see the raw data in air and the raw data on the fabric. So typically you cannot analyze anything when you have a look at the raw data. We have generated or invented a novel calibration method. If you're interested, please come to me later or maybe write me an email. It's quite difficult to explain it, but we get these calibration parameters, and by calibrate these raw data with these calibration parameters, we can generate these nice eddy current C scans. We find pins, so metal insertions. So if there's a broken needle, that's quite easy because its conductivity is much higher than the carbon fiber. We find fiber fuzz that can fall on the fabric. Therefore, we use also machine learning algorithms. So that's quite impressive how it works. So it's very easy to detect these fuzz balls. We measure the fiber orientation on the fabric, and therefore we use the standard 2D Fourier transformation. And here we see a typical report out of the machine, the orientation for each segment. Yeah, so short conclusion, we're using also machine learning algorithms to determine the gap width. So that's the most important thing for the machine. Gap width in 0, -, +45, 90-degree orientation. that's a short example. Yeah, we find all the foreign objects, and maybe one interesting thing. So we generate a PDF protocol for each role, and you as a customer maybe have then a role with a certificate and the PDF protocol where you can see, okay, there are some problems, or this area is correct, so I can optimize the cutting process. We also inspect recycled carbon fiber wales, so for its homogeneity. So that's an eddy current C-scan, and here we have the photo. So it also works on these very thin parts, and we also can use it as an eddy current strain gauge. So that's only a short introduction, so I will go quickly over this slide. So here we see strain gauge based eddy currents. So these are eddy current scans that were acquired during the tensile test, and you see slightly a contrast change, and this occurs because of the phase change over increasing mechanical loads. And with my last slide, I will hand over to Kilian. This is a typical hydrogen H2 pressure vessel, a dry wounded vessel, and we can also, yeah, I think you know it now. We can also inspect it with eddy current. We can generate these nice projection, and we see the orientation and even bigger gaps or smaller gaps. And yes, this full inspection takes over about 5 minutes. And with this last slide, I want to thank you for your attention and hand over to Kilian. Thanks a lot.
Yeah, Martin, thank you very much. My name is Kilian Tschöke. I'm working in the department for condition monitoring and testing service at IKTS, and leading the working group for model-based data evaluation. And now we've seen the process to investigate fibers up to the components, and now I will show you some examples for non-destructive testing and monitoring, mainly based on acoustic methods like ultrasound, coming from the component to structures. So if you to have a smooth transition for you, I want to also start with the pressure vessel. On the left side, you've already seen these results using the eddy current measurement systems, but you can also use ultrasound to investigate or to inspect these pressure vessels made of carbon fiber, maybe also made of glass fiber. And you can combine both methods, the eddy current and the ultrasound, into one inspection system. This inspection system is based on a roller technique. That means the ultrasonic probe is here in this roll and can inspect the pressure vessels. This inspection system was already shown this year, in the beginning of this year in Paris on the JEC. So how does it work? We can combine different probes. That means also different possibilities to detect defects. We can work with inner probe and an outer probe. This outer probe can be this roll, as you've seen in the picture on the previous slide. And by using different techniques for the coupling, for example, water coupling, and this figure here, of course, the vessel is filled with water, but you can also work only with a really thin film here on this roll. Or you can also use ultrasound, which is only air coupled. And by using this, you can detect different defects, for example, after manufacturing of such a pressure vessel. Defects could be delaminations, cracks, or changes in the thickness. And also, as you've seen, by using eddy current, by combining different inspection methods, you can also measure the fiber orientation, gap sizes, or the resin content in your component. Really important is, again, Martin already mentioned the calibration. This is not only true for the eddy current, but also for ultrasound. So the manufacturing process and the structure itself of the component, of the CFRP component, has a high impact and high influence on the signal to noise ratio, and so on your quality of the inspection system itself. So you have to inspect, or you have to do thickness measurements before calibrating your systems, and to get the best results for your crack detection. This customization is done here at IKTS, or can be done at IKTS, and can definitely improve the results of your inspection. And as mentioned, we can combine both techniques, the eddy current system and the ultrasound system, for this fully integrated inspection systems for pressure vessels to detect damage or anything else in the end of the manufacturing process of the component. And coming from the manufacturing to the operation of components, then we are not only working with NDT, with classical non-destructive testing, but also with monitoring. Monitoring means we want to install permanently some sensors on your structure to get permanently information about your structure, about your component in operation. For example, well, one example that we all know is a smartwatch, which is a permanently installed sensor on yourself, which measures data all the time. For composites, we use a special type of ultrasound. This means these are elastic waves in the range of ultrasound, so between 20 kilohertz and maybe 500 kilohertz or up to 1 megahertz. And this special kind of ultrasound comes from the relationship between the thickness of your component, the wall thickness of your component, and the wavelength. So the wavelength has a relation to the frequency, and so we also have a relationship between frequency and wall thickness of your component. It's in between the NDT, between high frequency ultrasound, like in the inspection system on the previous slide, and above the modal analysis, which is more a global detecting technique. And these guided waves, these ultrasound waves for plate-like structures, could be used in a passive mode and in an active mode. And therefore, I want to show you some examples. For both techniques, for the passive and for the active, you can use mainly the same piezoelectric transducers. So in most of our systems, we use the same transducers for both techniques. Piezoelectric transducers, as you can see here on the slide, different sizes, different shapes to be adapted to your structure. And these piezoelectric transducers excite and receive the guided waves, which are in the English literature well known as lamp waves. And on the right side, you can see this behavior that I've mentioned, that you have a relationship between wavelength of the guided wave and the thickness of your structure. For the passive measurement is also known as acoustic emission. That means your installed sensors, here on the figure, these blue dots, they are installed on your structure and they are listening all day long to your structure and listening to acoustical events and acoustical signals in your structure. These events may come from different loads or forces acting on your structure, but also coming from structural damage. So this means you're with your transducers, you are listening to the structure, you detect the ultrasonic waves in a specified frequency range, and then you will get the measurement signals and analyze them to localize the damage, to characterize them based on some features of the signal like frequency, amplitude, energy, and so on. And so you get information about the location of your damage and the possible cause of your damage. And finally, in a really nice visualization. The acoustic emission is a well-known testing method for pressure components, mainly for metallic components, to detect the growing of defects. but it can be also used in operation of structures. For fiber reinforced plastics, it's in use for more than 15 years, in the range from coupon samples up to components in the aerospace and railway technologies, or for automotive for CFRP wheels, and up to rotor blades, so up to really, really large structures for rotor blades of wind turbines. The active system is a little bit different. Active means now that we actively excite the ultrasonic waves into our structure. So this is not done passive by the sensor, so we actively excite ultrasonic waves. Here in this example, you can see a ring of piezoelectric transducers used for actuating, and then the other ring for sensing the ultrasonic waves. And if you excite, hopefully you can see these small blue waves propagating through the structure, you can get a signal from the actuator to the sensor on this path. And now if you start the next measurement the next day or next week or whenever, and there's a change in the structure, in this case a damage, then again we excite the wave into our structure, and the sensor measures the signal, but it also measures reflections and changes coming from the damage. And by comparing both signals, by comparing the signals from the undamaged component with your current measurement, you can also analyze these differences, these data, and for example visualize signals and cracks, damage, whatever in your structure. You can get also information about the position, about the size of the damage, and maybe the type of the damage. This active measurement has high sensitivity for detection of cracks, but also for delaminations in composites. Examples could be monitoring of pipelines, as on this slide. Also pipelines made of glass fiber, for example, made of composites. Could be used for hotspot monitoring. That means you focus all of your monitoring on one damage position, or one position, or one position in your structure where you expect damage. It's really sensitive to detect damage in CFRP panels, for example, in the aerospace sector, and can be used to visualize damage in different components. One really important question when we think about permanently installed sensors is, well, how to install your sensors, how many sensors do we need, and where to install them. Therefore, we have different methods, and on the example for the pressure vessel, for the automotive, we're talking now about type 4 pressure vessels with the loads up to 700 bar. Of course, they are made of carbon fiber or reinforced plastics, but damage, impacts mainly, are not visible on the structure, but may cause to failure of the structure. So one solution could be an installed sensor system that localizes damage. Here on the right side, you can see the same principle as on the previous slides. We measure in different conditions of the structure, the so-called good condition, the condition without any damage, and the condition with a damage in it. And then by comparing them, you can also get information about possible impacts on your pressure. In this example, we have different positions for the transducers. They are embedded, or they can be embedded even in the pressure vessel. But how to get these positions? Therefore, we mainly use simulations. That means we take a component, for example, made of carbon fiber. Due to the anisotropy, it also highly influences the propagation of our ultrasound in the structure. So therefore, we transform our real-life component into a numerical model. First of all, into a CAD model. Then we transfer it into FEM solution or an in-house. We also have an in-house software which is called EFIT to model the guided waves in composite structures. And then we can model different damage positions, different sensor positions, analyzing them by using statistical methods. For example, the known Barron's method, which is known from the aerospace. And by using this statistical method, we can get information about the probability of detection, which means the probability to detect a damage of a specific size on a defined location. And by knowing this, we can optimize our sensor network. We can optimize the sensor positions and the number of sensors to get the best probability of detection for defined sizes of damage. So we have to know the critical size of the damage, and then we can optimize our sensor network. After knowing the positions of the sensors, we can go to the next step and integrate them into our structure. This has a lot of advantages. For example, the transducers are protected against environmental influences, against fluids, again, also a little bit against impacts and damage from the outside. And different possibilities are possible. We can only integrate the piezo ceramic transducers. We can integrate also electronics, power supply, whatever is needed. But we can also design it in a way that we put all the electronics in a diagnostic unit, in a specially designed measurement hardware. So whatever is needed, we can only integrate the transducers, but also electronics, however it is needed for our application. Last example, back to the acoustic emission. Really nice, colorful slides in the end. This was an example of an acoustic emission measurement campaign during the design and manufacturing of a CFRP bogie and a railway. This bogie was totally manufactured of carbon fiber, and we've measured with acoustic emission sensors. Here in the right side, you can see the small acoustic emission sensors. The acoustical events coming during tensile tests, during bending tests of the bogie. And as mentioned before, by using different algorithms, we can localize and detect the events, the acoustical events in the structure. And so we get a lot of information about weak spots or possible damage in the structure. And now if I go through the different slides, you can see the hotspots here of the acoustical events, and color-coded is the number of events. So this means high red color means there are a lot of events in this region. So this means this region is a lot of under tensile under stress and maybe should be investigated further. So with this example, I will come to our conclusion. We've shown you different NDT and monitoring techniques that are already available. The eddy current system and ultrasound system and monitoring with guided waves. But to be honest, there are of course a lot of other techniques possible, also available. Phased array ultrasound techniques, ultrasonic microscopy and thermography. And if nothing is suitable on the market, then of course we at Fraunhofer could help customers to design testing and monitoring tasks. But in this presentation, we just wanted to give you an overview of some examples. And so thank you very much for your attention. And if you have further questions, we have now time for questions, and you can also send us an email.
Okay, then thank you very much, Kilian Tschöke and Martin Schulze, for this really impressive overview of state-of-the-art non-destructive testing and monitoring technologies for composites.
Thank you for the possibility.